Click the bell icon to get latest videos from Ekeeda.
Hello friends, welcome to the subject of machine design. In our last lecture, we have seen the difference between the thick cylinders and the thin cylinders. In today's session, we are going to derive one important aspect, that is Lamy's equation. Now this equation, as we have said in the last lecture, is the basis of solving or analysis of the thick cylinders. So let us start with the Lamy's equation. In the beginning, we will look at the assumptions that are made for this equation's derivation. So the derivations or the assumptions in Lamy's equation. Very first assumption, which is common for almost all the theorems, that is the material homogeneity. So your material of the thick cylinder should be homogeneous throughout its length, throughout its radius and throughout its thickness. So material should be homogeneous. When I say material homogeneous, it means all its properties, all its mechanical properties, right from elasticity, plasticity, etc., should be unique or same across all the directions. This particular consideration gives us the benefit over consideration over the whole body similarly or equally. A second assumption goes with this: the plane sections. If I take the section of a cylinder, the plane section remains plane even after the elongation. That means plane sections remains plane even after their elongation. Which means, let us consider a cylinder. Let me apply some forces. Definitely stresses will induce in them. Let me apply some internal stresses. Again some stresses will be there. If I take a section in this manner, even after that the plane surface will remain plane only. So this is the second part of this section. That means this particular surface will remain plane and it will not distort. That is my second assumption. Let me move on to the third assumption. It says that since the planes are planes even after the section, we know that the strain that gets generated is uniform. So with this assumption, there comes an important equation which we are going to write now. The equation says that we know that strain is equal to 1 upon E, that is Young's modulus, is equal to the stress in the direction O minus the stress in the direction X divided by this particular term, as we know, is Poisson's ratio. Yes, 1 upon M is Poisson's ratio, plus the stress or the extra stress that is applied in the X direction. I'll call it sigma X dash divided by Poisson's ratio. This particular thing remains constant. This particular thing remains constant. Now, naught is just any one direction. It can be X, Y, Z, but we have denoted it with naught. Fine. So with this assumption or with this equation, we are going to derive Lamy's equation further. Let's move ahead. There comes sigma X. Yes, of course, we need to understand what are the components. Sigma X, I will call this as the Px, or sometimes we use the letter Px also, but it remains the constant. Second thing is sigma X is circumferential stress, or we'll denote it by sigma C. Sigma C. Next thing is sigma X dash is radial stress, so we'll denote it by sigma R. So like we said, sigma radial or radial stresses are prominent in thick cylinders. So that's why we are going to consider this particular component, and the same component we have considered over here. Earlier we used to have the equation only up to this, right, for the thin cylinders. In this case this is just an additional term. Let's move ahead. Now the theory is related with the thick cylinders, so there is a considerable thickness. So in such case, let us draw the cross section. Now we are actually entering into the derivation part. Let's consider a cross section. It's a random cross section. Let's consider it's a circular cross section. Now there is some internal pressure applied. Now of course this is a thick cylinder. So once this internal pressure is applied, everywhere the stress distribution goes on happening. We know that the stress distributed up to this limit is different than the stress distributed up to this limit, because it's a thick cylinder. In case of thin cylinder, we used to consider that the stress that is distributed right from its inner diameter to the outer diameter is uniform. And that's why we need to consider any random strip inside this. Let's consider there is a strip inside it of some infinitesimally small thickness. So let me draw the only strip. Now this is merely the strip that we are going to consider. It has got some thickness which is very small in nature. Let us denote it with dx. So dx is the small thickness. Now let us assume that inside this strip that we have considered, the pressure acting is actually radial pressure, of course, and let us say it is sigma r. So that radial pressure which is acting inside it is going to vary on the outside. That is what we have seen. So the stress that is acting exactly at the outer layer of this strip will be greater than this. So let us say it is sigma r plus some delta of sigma r. So some varying radial stress, small amount marginally greater than that. Now this is one aspect. What else we have is there is circumferential stress also acting. So that circumferential stress definitely will act along this edge. So that circumferential stress that is acting over here will be your sigma circumferential or sigma hoop. So this is an additional stress which is circumferential stress. So we know that circumferential stress that is acting over here has to do something with its length and the small strip that we have, so that is dx. Apart from this, let us consider this as the radius of the strip, the inner radius, of course. Now guys, you need to understand that the internal pressure is the actual source of stresses. Internal pressure effectively acts, or it acts with more intensity on the inner surface, and that's why always the inner diameter is more prominently considered for the design. And that's why let's consider the inner radius, which is x in this case. And just because it was x, we had considered this thickness as dx or delta x, and from there we came across this particular stress. So this is your radial stress that is acting on outer side, this is your radial stress that is acting from inside, and this is the circumferential stress that is acting over this section, right? If you remember, we had this kind of section for the cylinders. So on this section your circumferential stress is actually acting. Fine. Now with this assumption, there comes an important aspect, and that's called bursting force. You might have seen this somewhere, that the pipe which are carrying the gases or which are carrying the water or any other fluid, they get bursted, right? So bursting is a mean of failure for different thick cylinders or thin cylinders, or let us say just cylinders. So we need to design them for bursting also. So the bursting force actually is the force which goes slightly above the equilibrium force. So we need to talk about the force up to which the equilibrium is possible, and after which the bursting is going to happen in case of cylinders. To be frank, in this case it's thick cylinders. So using that equilibrium condition, let us derive the equation for bursting force. So the bursting force will be given by, it gives me the idea that it's my radial force or radial stress into twice the radius into L. If you remember this, this is a circumference or the length of circumference, minus, it gives me again radial stress plus the delta, the outer one of course, delta radial stress. This is one aspect, and the remaining aspect into twice the x, which is radius again, into delta x into its length. So with this, if we elaborate it, if we solve this particular equation, we will get this one. We can take 2L common, that makes it minus radial stress into delta x minus x delta x minus delta x into delta radial stress. Now this is the prominent equation we have got for the bursting force, but this is not valid for the whole cylindrical strip. This is valid for only a small strip which we have considered at certain radius, that is x. Fine. Now using this, we are going to integrate this part, because we know that when we consider it for very small strip, upon integration we will get it for the whole domain. So next thing we are going to do is, there's one more thing. If you see, these two are very small quantities. Small quantities, when we take product, that goes to even smaller number, so we can neglect them. So neglecting these small entities, will get the next expression, that is bursting force is equal to minus 2L into radial stress into dx plus x into delta radial stress. So that's the final expression when I neglected the product of smaller entities. So with this, when I move ahead, I'll get resisting force. Now we know that the force that induces inside the material that resists the change. Here change is occurring because of the bursting force. So bursting force will experience a resistance given by the material. So that resisting force that we know is 2 times its circumferential stress into the length into delta x. Why 2? Because we have got two sides on it. Fine. And hence, for equilibrium, we need to equate these two. We know that when this resisting force will be equal to the bursting force, there will be no bursting happening, right? So in that condition, we can say that the cylinder that we are considering will be in equilibrium. And for that, we can say that has to be equal to the expression that we have obtained from the previous part. Or in short, when we cancel out the terms, we will get the answer in this manner. Circumferential stress is equal to minus this sign outside, your radial stress, plus x into delta radial sigma divided by delta x. So this term is nothing but the variation of radial stress across the variation in the radius. That is what we had discussed. If you recollect it, we had said that the radial stress will go on changing across the thickness of the thick cylinder, and that's why this particular term comes into picture, where the radial stress sigma r goes on changing with respect to the change in the radius. Fine. So with this, let us advance. So this particular theory is called Lemay's equation theory. Let us put it in proper words, which says that the limit of thickness where the product will be in equilibrium, or the thick cylinder will be in equilibrium, is given by, so we talk about basically the limit of thickness is given by circumferential stress plus your radial stress plus a particular radius, change in your radial stress with respect to change in your x is equal to 0. So this equation becomes equation number 1. Now the next thing comes when the relation that we obtain from them is, if you see theoretically, radial stresses are considerably smaller than the circumferential stresses. So it was observed that the difference between circumferential stress and the radial stress is equal to twice the A. A is just a factor, any other factor, and that we need to find out. So there is always some relation that lies between the circumferential stress and the radial stress, and that difference is given by some constant term. That term we are going to recollect, and hence we can say that sigma c is equal to your radial stress plus twice the A. Sigma radial stress and twice the A. So this is an important aspect that is obtained from these two equations. Now let us put this expression in a first equation that will give us the final expression becomes your sigma radial plus twice the A plus your sigma radial plus x delta change in radial stress with respect to the change in length is equal to 0. Now again let me recollect that this particular expression which we have obtained is for the small strip that we had considered. It's for this small strip which we had considered. Fine. So when I move ahead, it gives me another form of expression that gives, of course, the earlier thing was the fractional derivation. So let us go for the better derivation that gives me change in radial stress divided by, can you see the operator has been changed now, with respect to change in radius is equal to twice the, of course, minus sign will be there, sigma radial plus A, which is a factor, divided by x. Using this particular fraction, we will get, we are just taking cross products of them, has to be equal to dx upon x, which is minus its sign. So upon taking the cross multiplication, we get this particular factor twice. Now we know that this expression again is valid for only the small strip which we have considered. Now upon integrating this particular small strip, we will get, on integrating, it's a natural logarithm. So log to the base e, we will get sigma r plus a, which is equal to minus log to the base e again of x square plus log to the base e again b. Now after rearranging the logarithm, of course they all base to e, after rearranging the logarithm we will get the final expression that says sigma r is equal to a factor b divided by x square minus a, where the factor b can be found using this, and that says it is log to the base e b upon x square is actually the ratio of log to the base e sigma r plus a. So this is what the final equation that we are going to use. This is the final equation that we are going to use for the analysis of thick cylinders. So this is nothing but the final equation given by the Lamy's theory for thick cylinders. There is one more aspect that we can say, that we know that there is a difference between sigma circumferential and sigma radial is equal to twice the A. So let me recollect the formulae for thick cylinders as far as the Lamy's equation is concerned. This is one of the equations, and the second equation which we right now have used is sigma radial is equal to b divided by x square minus a, and on the same lines we can say sigma c is equal to b upon x square plus a. Equations 1, 2 and 3. So they form the basis of analysis of thick cylinders. So there we concluded with the Lamy's equation that is used for the analysis of thick cylinders. In next video, we'll be looking at how to solve the problems of thick cylinders, design of thick cylinders. Thank you so much for watching this video. If you like this video, please subscribe to Ekeeda. Thank you. See you.